So the 5-minute version on recap of 13.1 is basically that we'd like to know something about flow in channels. Flow in channels, of course, can be exactly the same as flow in a pipe, as you see in this little figure. The difference is that it's driven only by gravity, not by the pressure, because you can't exert a pressure between the upstream and the downstream because it'll just blow through in the air. In the same way that when we talk about pipe flow, we can characterize behavior in terms of Reynolds numbers. But Reynolds numbers are typically defined not in terms of a hydraulic diameter as our characteristic dimension, but as a hydraulic radius, which is equal to 4 times the diameter. And so since it's 4 times the magnitude of the characteristic length, then the magnitudes of the Reynolds numbers where turbulence becomes place is a factor of 4 different. The bottom line being that for any open channel flow, it's likely that it's going to be turbulent. And so if you remember from when we talked about Moody charts, and we talked about friction factors versus Reynolds numbers, they looked something like this. Then almost always for open channel flows that were in this region where it's turbulent, and therefore the magnitudes of this friction factor, which is actually called Manning's N factor, as we'll see, is a single value, right? These lines are horizontal. And so that's the corollary with pipe flows. And so when we talk about open channel flows, they come in a variety of flavors. And the one that we've already talked about in 13.1 have been what are referred to as uniform flows, UF. And the essence of a uniform flow is that if you look upstream and downstream at the depth of the water, then by definition for a uniform flow, both of these depths are exactly the same. If these depths are exactly the same, then the cross-section of flow has to be the same, and then conservation of mass requires that the velocities are the same, which requires that the velocity heads are also the same. If the velocity heads are also the same, then the energy line, which is this green line here, and the slope of the bed is what's driving flow. Gravity is the only thing that's driving flow. Then they have to be parallel. So the slope of the bed, the slope of the water surface, by definition, by y upstream and y downstream being the same, and this energy surface all have to be parallel to each other. And if they're parallel to each other, then that basically is the definition of uniform flow. And that's the easiest one to deal with, and that's the one we dealt with in 13.1. If we look at non-uniform flow, then the upstream and downstream depths aren't the same, and therefore the velocities at these points aren't necessarily the same, and therefore the energy grade line may deviate from the others. They may not be equal to each other. And so what we've dealt with already are uniform flows, but we will now deal with the cases where we have what are referred to as gradually varying flows and rapidly varying flows. R is for rapid, G is for gradual. And they are exactly what they say. They're where the depth of water as you go downstream changes in some either gradual way or very rapid way. And we need other concepts to be able to deal with them. But just to close out our concepts of open channel flow for the uniform flow, it's basically pipe flow. You can think of flow in a pipe where we have this velocity profile. When we look at open channel flow, we basically cut this velocity profile so that it's uniform, and so that the area under this graph for this red line would be the area underneath this, so that the volume flow rates match up. And that's what we assume for pipe flow. And what we do is we... Oh, is that beer? If it is, you should share it. What we do is we basically look at conservation of momentum, and we look at, you'll recognize this. This says that the shear stress acting on the bottom of this channel as we go from upstream to downstream is some factor multiplied by a velocity kinetic head term, velocity loss term. And so if we equate this shear stress with the shear stress that we get from doing the force balance on this momentum balance on this prism, then we end up with an equation. And just like the pipe flow equation, all you need to know is it looks like this. It is either an average velocity in the channel, which is uniform within the channel. If you multiply that average velocity by an area, then you get a flow rate. And this flow rate is a function of the slope of the bed of the stream. This is S0. In other words, it would be if you just look at this. So this would be, if you like, this would be Z1, this would be Z2, this would be L. So I think in our language, the slope of the bed is equal to Z1 minus Z2 over the length, nothing more. And so the velocity, not surprisingly, if you increase the slope, it goes faster. The hydraulic radius is defined as the area divided by the perimeter. The wetted area, the cross-sectional area divided by the perimeter, I think. And N is our friction factor, or Manning coefficient. N is equal to Manning, who is the guy along with Chézy, a French engineer, who came up with this idea. So you'd imagine that if N is larger, if it's larger, it will make velocity smaller. So larger means rougher. So a high value of N equals a rough pipe or a rough conduit. And so in this little table below there, you can see a whole bunch of them. So if you see clean and straight, let's see. If you're flowing, where's excavated earth channel? So clean earth channel, one with stones and cobbles. This is small, this is large. So it's just a resistance factor. So it bears on the fact that if we have, we can define behavior as being turbulent, then the magnitude of this Manning coefficient, which is N, is just a function of how rough the boundary is. So you look at your channel, you see what it is, and you decide on what N is. So it's formulaic as well, a recipe. So velocity of flow is a function of how steep the bed slopes, how big the hydraulic radius is. You'd like a large area to a small surface area, which is really what hydraulic radius is. The area is the cross-sectional area of flow. The P is the wetted perimeter. K is just a dimensional factor which you need to add in, which is 1 meter per second if it's SI units, which we use, and it's 1.5 if it's feet per second if it's in English units. So these equations are not, they're the one equation that perhaps we've dealt with which is not dimensionless. It matters what units you use. So you should use, this would be an area divided by a length, so this would be in units of meters. This would be in meters per meter, so this is dimensionless. This is in meters per second, and this is dimensionless. And so the velocity comes out as a function of that. And so as a function of that, you can get either the velocity of flow, multiply the velocity by the cross-sectional area, and you get the flow volume. Nothing more than that. You can do it for composite channels just by summing up the components, by using some weighted average of the Manning coefficients. If you have a deep channel and a shallow floodplain on the sides, for instance, they would have different Manning's coefficients. You could figure out that if you get a really wide channel that's just the same depth, and it actually reduces to being almost a one-dimensional form. You can use compound channels to be able to add together the influence of water going down A1 into the board and down A2 and down A3, where the total volumetric flow rate is just the sum of the components going down the first channel plus the second channel plus the third channel. Typically the slopes would be the same, but the hydraulic radii and the areas would not be the same, nor the Manning coefficients necessarily. And so in each of these, the area would be this cross-sectional area here for A1, and the perimeter would be this length around the side, right? Not this dotted part, because that's all flowing downstream, hopefully at roughly the same velocity. And so you can sum up those components. Okay? And so it's kind of formulaic. I won't go through the examples. You can look back at last week's 13.1 to be able to see how to do that, but that's basically the idea. The basic idea is you can use pipe flow concepts to be able to do it and figure out what the volume flow rates are as a function of a friction factor, which we now call a Manning coefficient, which is representative of the fact that it's always turbulent flow, and therefore it's constant magnitude irrespective of the velocity, so you don't have to worry about that. Some cross-sectional area, a hydraulic radius, and that's it. And a bed slope, I guess, which is driving it. So no pressure is driving it now, it's just the inclination of the bed. And you have to take account of the appropriate magnitudes. So do remember that those formulae that we deal with are not dimensionless. They have dimensions in them, and you have to be careful to use the right formula. Okay. All right. So that's what we've talked about so far. So that's our longer than usual recap, which says that the depth of flow in the water as you go downstream doesn't change. That's our definition of uniform flow. So I guess UF is what we called it. So of course to do that we have to make an assumption. We have to make an assumption that when we look at this ditch that the flow is uniform. And how do we necessarily know that before we run water in our ditch and look at it and measure the depths? And so the other kinds of flows we have to deal with are these two others. One is gradually varying flows, where the depth of water as it goes downstream is not zero, but it's a very small number. And the other case that we'll deal with are rapidly varying flows. And we'll see that when we deal with those, the depth change with going downstream is a big number. And these would be things like hydraulic jumps. When all of a sudden you're going along slowly, actually quite quickly, and the depth of the water jumps up to being twice the height. And if you look at 13.1, please do, you'll see we have surfing West Virginia videos going there. So the waves that people surf on in rivers are just manifestations of rapidly varying flows. So we come back to this same figure again. We've dealt with this. So we've dealt with these uniform flows. So now we're going to talk about the concepts we need to be able to understand for gradually varying flows. And so there, this case on the right-hand side, whereas you basically go downstream, the depth changes. And if the depth changes, then the velocity presumably at this point changes relative to this one. And therefore this v squared over 2g term here will also change as you go downstream. So the idea is that the slope of the energy surface, the slope of the water surface, and the slope of the bed aren't necessarily the same anymore, and which was not the case for uniform flows. Okay, so that's a scratchy diagram, but it makes the point of where we're going with this class. And what we have to do is we have to define this behavior, which is called, we'll use Bernoulli's equation, or we'll use the energy equation, to define Bernoulli in a slightly different way and to think about it in a slightly different way, which will be important for us. And that will allow us to be able to define behavior other than uniform flow, which is what we've just done, where really the only two things you need to remember are these two very basic equations and how to use them. So these are the cases that we want to deal with: gradually varying flows and rapidly varying flows. And actually we can, as we've alluded to, we can define the behavior in terms of this change, how severely this depth of water changes as we go downstream, and we can define it in terms of these slopes that we have. The slope of the energy line and the slope of the bed. Obviously we don't necessarily know the slope of the water until we do our calculation. So this is the energy line. Sometimes we call it EGL, energy grade line. And this is the slope of the bed on the bottom. And this is the Froude number. And we haven't really revisited that lately. It's one of our three favorite non-dimensional numbers. It's the ratio of the velocity of flow divided through by the velocity of the celerity wave. Remember, we used that when we looked at tsunamis, and we'll revisit that in a second. And we know that the velocity of the celerity wave is equal to gravity times the depth of flow, and square root of gravity times the depth of flow. So you can work out the units for this. This is meters per second squared times meters. So meters squared per second squared. Square root of that is just a velocity, right? Meters per second all squared. Square root is just a velocity. And so this is an important parameter for us. It's surprising that it would be the wave speed, the surface wave speed that's important to us, but it is. So let's very quickly revisit that. We talked maybe the first or second time we met about wave speeds. We talked about the Japanese earthquake, the idea of putting ocean bottom sensors on the seabed so that when a fault goes off, the acoustic wave that runs through the solid arrives at comes at 5,000 meters a second, 5 kilometers a second, so arrives there very quickly. You take that information, you send it on electrical cable, which travels, of course, at the speed of light, to the coast. When it gets to the coast, you know that something's happened 100 kilometers away, and you sound the alarm, and you wait for the other things to happen. If the earthquake travels through the solid at something like the speed of sound in rock, which is about a couple of kilometers a second, then to a couple of kilometers a second, then you know how long it will take if you're 100 kilometers away to be able to get there. Tens of seconds, maybe minutes, a minute or so. And so you get the early warning, so you walk out of the building and everything's hunky-dory. But the wave that goes through the water comes in two forms. One form is the wave that if you're shouting in water, underwater, if you can manage that you'd hear it at. When that comes quite quickly, it's slower than the speed of sound in something really competent like rock, but much faster than the tsunami wave, if you like. So it would arrive a little later, and you can do the math for 1.5 kilometers an hour, a second rather, to go 100 kilometers. So I guess it's about 100 seconds, right? Something of that order. This is the speed of sound in air, which is even smaller. It's because air is less stiff than water, surprisingly. Perhaps not surprisingly. But the one we're interested in is this celerity wave. And the celerity wave is the velocity that the water travels on the surface, from the down throw actually the up throw from one thrust going up. It pushes up the water. You get a water cliff develop as one side goes up, and that water cliff then radiates away from it. And we saw from looking at the videos, it takes something like 20 minutes for it to go 100 kilometers. And so you just wait for that to arrive. So we won't go through the derivation of this, but we will note the fact that this celerity wave is, we've already written it down, is typically equal to gravitational acceleration times the depth of water, by definition. We didn't derive it before. We don't really need to derive it now, but we'll just take that on trust. And it turns out that if you look at the velocity of this celerity wave, what this says, this is a plot of what the celerity wave is as a function of the depth of the channel relative to the wavelength of the wave. And if the depth of the channel is small compared to the wavelength of the wave, say you're in a river, then it turns out that this is a pretty good approximation for the velocity of the wave. If the wavelength is, if it's very deep compared to the wavelength, and the wavelength may be kilometers in size for an open ocean wave, but if the sea is 5 kilometers deep, then it turns out that this isn't such a good approximation, and the wave speed is less. But we don't need to worry about that. So it changes with the depth of water, but we can calculate that. So the key issue here is looking at these behaviors. So we think that for these rapidly or gradually varying flows, it matters what the velocity is, and it's suggested by this one little equation we looked at. But the idea here is if you drop a pebble in water and you look at the waves that emanate from that, you get ripples that would look like this, and those ripples would move out at some velocity, which is this depth of water multiplied by gravity. It doesn't vary with the kind of fluid it is. If you're dropping it into mercury, it would be exactly the same as if it was water, because no behavior relative to the fluid is included here, just that it's a liquid. So if instead of dropping a pebble in and looking at this wave train as it goes out, you plink it once a second, and so it makes a mark. It's kind of like, so that at each second it made a little impact, and there was a single wave that went out from that one impact, then you'd also get something that would look like this. If you then, in addition to having a static bucket of water, you allow that water to move, like doing that below a bridge where you have a stream flowing underneath you, then you'd see something different, right? You'd see a plink in the middle, which is what you do at this instant. That would slowly move out, but it would be a concentric circle. But the location of that concentric circle, say after 5 seconds, this would be a circle on the outside, but no longer would it be centered on the point where you did your plink, right? Because it's physically moved downside. The water where you put your finger in and made this move has now moved x feet or x meters downstream, and of course the distance it would have moved downstream would be what? This length would be equal to the velocity of the stream times the time since you plinked it, right? Nothing more than that. You can imagine if the wave velocity that it travels out from here is exactly the same as the velocity of the stream. So if the v of the celerity wave is exactly equal to the velocity of the stream, then you'd end up with something like this, right? This would be the circle that you put in 10 seconds ago. Its center would be here, but where you plinked it was exactly at this point where you're plinking right now. And so if the velocity of the wave traveling in the water and the stream traveling downstream is exactly the same, it's kind of this relative motion thing that we've plinked it. The water that we plinked is now here, but the radius that this has gone out to is exactly where we're making this disturbance. And so the Froude number for this, by definition, since the Froude number is equal to the velocity of something divided by the velocity of the celerity wave, by definition is equal to 1, right? And so you can think of this as, it's like flying at the speed of sound, right? If I'm flying away from you at the speed of sound, then you'd be happy to hear that you'd never hear a damn thing I said. And that'd probably be very nice for you. And if I was going the opposite way, it would be different. But that's basically the idea. So this is moving downstream, trying to communicate upstream, but the information just doesn't go any further than the point where you send it. And of course, in the case where the streamline downstream velocity is larger than the celerity wave speed, then these would just look like separate circles as you go downstream. And so there are these fundamental behaviors which are different from where we have the Froude number less than 1, which means that we end up with this, and the Froude number greater than 1, where we end up with something that looks completely different. And so you might think that therefore in these different flow regimes you'd end up with different behaviors, and that's kind of the essence of this idea of gradually varying flows. And so pictorially this is exactly what it looks like. And so the one thing that's important about open channel flows is that you basically have this extra degree of freedom. So you have water that's going along, and we're not telling it how deep it could be. It could be this deep, and so if you want to get a specific volume of flow, it could be quite deep and flowing very slowly, or it could be very shallow and really scooting along very quickly. You have the same volumetric flow rates. And so you have this extra degree of freedom that is the height of the flow, which allows it to be in a variety of different conditions. It can bifurcate, if you like, is the mathematical word, between different flow regimes. It can be either a quiescent flow regime, which is flowing slowly, or it can be a very fast flow regime, which is very thin, which is fundamentally different. And they would have the same volumetric flow rates in this, because this is going really quickly but shallow, this is going really slowly but less shallow. And so we can get, it turns out that we can get these two behaviors equally easily, and we have to make a decision to figure out which behavior will it prefer to be in. And will it change as it goes from upstream to downstream, from being this fast flow to being this fast shallow flow to being a deep slow flow, which would satisfy the fact that the same volumetric flow rate goes down. So the celerity wave is important to us. And it's really important to us because, as we'll find out, I guess it's too early to do that. We'll find out that this Froude number makes this distinction between these two different regimes of flow, which we'll call supercritical, which is the really fast but thin flow, and subcritical, which is the really deep but slow flow. And they're bounded by a behavior which is critical, which, perhaps at no surprise, is exactly at the flow rate where this occurs. And it's all related to whether it can communicate its information upstream, right? If it's flowing downstream, there's no information that goes upstream of this point because it can't travel right there. It can't get information up there. In this case it can, in this case it can, and certainly in this case it can't. It can't even get that information downstream of this. Okay. So what we need to do then is to look at the flow down a stream. And the idea is that we can take a flow which is a deep flow upstream, a less deep flow downstream. The bottom of this bed has some slope to it, which we'll call S0. We've already called S0. And if we wanted to write Bernoulli at each of these points here, this upstream point and this downstream point, points 1 and point 2, then we could do that in terms of everything we have on this diagram. We have an average flow velocity, downstream and upstream. We have a velocity head term, v squared over 2g, downstream and upstream. This defines the energy grade line that we've talked about before. This is what we've called the EGL. And included in this the fact that this EGL is not horizontal. If it was horizontal, it would be Bernoulli-like, right? No head losses, no viscous losses in the system. If it's sloped, then this head loss is exactly what we had in the Bernoulli equation. So the Bernoulli equation, of course, with the head loss term is the energy equation. And you've seen it many times, written the way I like to do it. Hopefully you like it that way as well. In terms of heads, all these are lengths. Pressure head, velocity head, elevation head. Upstream, the same downstream, and also some loss that's in here. And all that the stream flow equations, well, it's not stream flow, open channel flow equations are, is that we now write Bernoulli slightly differently, or the energy equation slightly differently. We write it in terms of the fact that we know that the slope of this bottom thing can be defined in terms of the elevation change of the bed between upstream and downstream over some length. So in other words, this term here and this term here, we can substitute just by putting this term here in, right? Just by rearranging it. What else? The pressure term. We know that the pressure at this point is just going to be the height of water. So the pressure at point 2 is just going to be equal to the depth of water, rather, multiplied by unit weight of water. So we could substitute that in as well. And we're going to be left with the velocity squared term, and we choose to write this head loss term as also a slope, right? So the head loss term would be equal to what? Head loss would be equal to the head loss is going to be equal to this divided by the length over curves, right? So in the same way that we write this term as being the change in elevation between these points as a function of the length over it occurs, This we look at the change in elevation of this energy grade line as a function of the length over which it occurs, and we just define that. So now we have our system defined in terms of a slope of the energy grade line, a slope of the base of this, the depth of the water upstream and downstream, and the velocity, those terms. And so if we make those substitutions, let's not belabor the point, we end up with a different equation which looks like this. The depth between upstream and downstream, the velocities upstream and downstream, the slope of the energy grade line, and the slope of the bed surface, which we know. So it's just a different way of being able to write Bernoulli. If we don't have any, if it's a flat, if it's a horizontal bed of the river, and we're not getting any losses in the river, both of these terms are either zero, or in the case where the energy loss is equal to the gradient loss, that'll also equal zero as well, right? In which case Bernoulli, for the case where we don't have, where these things exactly balance, will just be given by this equation. Upstream depth, downstream depth, upstream velocity, downstream velocity. Which one's which? This is one, right? Or is it? Should be symmetric, I would think, right? Yeah, no, that's right. That's right. Okay. So this is one on here. Okay. So all this is Bernoulli's equation written in a different way. And so don't worry too much about that now. But what it allows us to do is we can take this term, which we're going to call, if you look at these individual components. So now the big important feature which is describing our behavior are these quantities. So there's y1 v1 squared over 2g, and there's y2 v2 squared over 2g. And so individually we'll call this specific energy of flow. And so we can, if we wish to, we can write for Bernoulli's equation where we modify this one to keep in this parameter here. So Bernoulli means what? So Bernoulli means viscosity is zero, so the head loss is equal to zero, and in other words, our way of saying that is that this energy grade line term is zero. So if we write it for that case, so in other words, we get rid of this term, this goes to zero. If we do that and we write out this equation in terms of this new parameter E, energy, you'll see we have this. This is what results. This is saying that the energy upstream is equal to the energy downstream minus the change in elevation as you go downstream. If you want to write this out in terms of how we define S0 is just equal to Z1 minus Z2 over L. It's just the change in height over the length. If you substitute into this, this is the best way to remember it. So always think of it in this term, this way. So this is the energy equation where all we've done is we've written it in terms of this different parameter, and this parameter E, specific energy, involves two things. It involves the depth of flow and it involves the velocity. So why do we do that? The reason we want to do that is because we can really put it into a single term that is important to us. So we know that when we flow water in a channel, we have an overall gross flow rate, volumetric flow rate. So this would be in meters cubed per second. If we take the width of the channel and we look at the flow per unit meter, per unit width, I guess, then what we could do is we could take this parameter, which we would know, and we know upstream and downstream would be the same, right? It has to satisfy continuity. Volumetric flow rate upstream has to satisfy the volumetric flow rate downstream if we're not losing flow. And we can conveniently just divide it through by the width of the channel, and we get the flow per unit width of channel. if we figure out exactly what this volumetric flow rate is, it's just going to be the flow velocity multiplied by the area. The area is just equal to the depth times the width, right? Velocity times depth times width gives you a volumetric flow rate, and divided by this just gives you velocity times depth. And so what we can do is we can take this magnitude of velocity and substitute it into this energy equation. And if we do that and we rearrange it, the bottom line, the punchline, that you don't have to remember this manipulation, is that now we've written the specific energy in terms of a flow rate per unit width of the channel. And so now this is the energy upstream or downstream is equal to the depth of flow plus the flow rate per unit width of the channel squared divided by gravity and by the depth of the channel squared. So in other words, we've taken out the velocity term here, which isn't very useful to us. We've replaced it with a flow rate term, and we now have it written in terms of one parameter, which is really just this width of flow, depth of flow rather. Okay, and so that's useful to us. It's kind of a convoluted journey, but the journey is for this reason. So now we have a single parameter that if we want to say what's going on upstream, we have a value of E1 upstream, and we have a value of specific energy E2 downstream. That completely defines our flow behavior. And we have that defined in terms of a single parameter. So what we could do now is, since we know that this is an important parameter both upstream and downstream, is we could look at how that behaves. And so we can take this parameter. So hopefully you don't dispute that this exists. This is exactly the same equation as we have here. What happens if we subtract off energy on both sides? So then this term goes to 0, and we end up with this term here. And what happens if we multiply both sides by y squared? And so then we lose this. And the reason for doing that is now that we have a cubic equation. So depth cubed, no depth in this term, this is just a constant, and depth squared equals 0. And so that's exactly this expression here that you see here. And so we know that for any cubic expression, it has 3 roots. And so, for instance, if we plotted the value of y, which occurs here, as a function of energy, which we have here, then we'd end up with a curve that looks like this black curve here. And so we're just taking a whole bunch of combinations of this. And because it's a, a cubic equation, we know that a quadratic has 2 roots, a cubic has 3 roots. And so for any given value of energy versus depth, so we only have 2 parameters in here, energy versus depth, and this curve is for Q equals something. I guess constant might be a better word, right? Q is constant. I guess it says that right here, I suppose, right? Then for any given value of this E, energy parameter, there are 3 roots. One root is here, one root is here, and one root is for negative depth. So this is a depth of 0. And so the punchline is that this negative root, I don't really know what it means, but it's not relevant to us. But these other 2 roots are the potential depths at which flow could occur. Either flowing at this shallow depth here, shallow because it's a very small value of y, and if it's shallow, to have the same volume flow rate, this has to be going very quickly. So this would be the fast one. Or it could be relatively deep, and it could be going slowly. I guess it'd be slow velocity, right? Not slow Q. Fast velocity. And so that's what is referred to as a specific energy versus depth diagram. And it says something about what we haven't really had to deal with that yet, and that is that if we have flow occurring at some volumetric flow rate downstream, because it's free to choose how deep it is or how shallow it is, it could either be at this behavior here or this behavior here. It's for it to choose in some respects. But we know that it has to be either at one or other of these. And if we skip back a couple of pages, that's exactly what this is saying. If we look at the diagram that we have, then this is the energy of flow, this is the depth of flow. We have this one line which is actually y is equal to E. That's telling me to go somewhere in a minute. And this is the curve that we have, right? So you remember this. We're flowing at a specific energy. And so we could either be at this point or this point. This point, obviously here, number one would be this. This point, in terms of depth, I guess y2 would be this. This is y2. So it allows us to be able to solve the problem in terms of what we're dealing with. So the water's free to figure out how it wants to flow. It knows it has to flow at a given flow rate. So Q is constant for this curve. And actually this curve embodies everything we've talked about today that's important in this little segment of what we're dealing with. This is constant flow rate is this curve. So it represents all of the cases it could be. It has specific energy in this flow, which we'll figure out how to calculate later. And it could organize itself either this behavior, which is this on the right-hand side, or this behavior on the left-hand side. So this would be a low velocity and a deep flow. This would be a high velocity and a shallow flow. And now we have to figure out exactly which one it would choose to do and why it might switch between them. I guess the other thing that we won't derive but we'll mention, which is very important, is that this nose here, this rightmost point, and I'll perhaps is where this is 3. This is where the Froude number is equal to 1. So the other important ordinate on this is the Froude number is equal to 1. And so by definition we said that flows that are very fast are called supercritical. Then this would be supercritical. And so the Froude number would be greater than 1. And this one would be subcritical. And the Froude number would be less than 1. So a little bit complicated, but step back from it and understand the important things are. The important things is have water going down a channel. It's got this free surface, which is kind of an independent variable. It's an extra degree of freedom, if you like. It could either be shallow and going really quickly, or it could be deep and going very slowly. And it can choose, in some respects, how it organizes itself to do that. And the definition of those two flows are these two individual points that exist here. And it really all comes just out of applying the energy equation, which is just Bernoulli equation with some components. So I think this figure is exactly saying what we've just said. This is the subcritical part, a very deep flow, but quite slow. This is the supercritical part, a very shallow but fast flow. And the nose on this is the so-called critical depth at a minimum energy. This is the minimum energy in it. And I guess the other thing that we might mention just before we close is that this coordinate is equal to this. So E min, write this down. Well, no, that's not in order, but you might, is equal to the critical depth times 2 over 3. And so in other words, the ordinate of this nose, it's a very important point, where the Froude number is equal to 1, is given by this equation. And we won't derive it, but we could do if we wanted to. I'm sure you could do if you wanted to. And so what we have is this interesting plot which says something about it. And so maybe we didn't get as far as I wanted to today, so maybe next time we'll talk about how we might use this to say something useful about how we choose whether it organizes itself as a shallow fast flow or a deep slow flow. And of course these are the things that you might have seen. Go back to 13.1 and look at hydraulic jump, because that's exactly what a hydraulic jump is. Water going down very quickly, all of a sudden becomes a big pile of foam moving much more slowly. So, okay?